some region of space and assume that it's a uniform field. Let's say I have a magnetic field that looks like this. How do I get a field that's uniform if I only have dipoles, you might ask? And the answer is you have to have a lot of magnets and you get vector cancellation just like you got with electrical charges, right? So somewhere over here off screen, we got a bunch of magnets over here that have north poles from which these field lines emanate. Somewhere over here are the south poles of those magnets. They're going to curve around at some point. But what we're saying is in this region, we've arranged our magnets really, really cleverly so that we get a nice uniform field that looks like this. Okay. The symbol we use for magnetic field is a B. Actually, I think they just chose this alphabetically. I think Maxwell did this. We can't use an M. We've changed most of Maxwell's other notations to make them make sense. We can't use an M because we already use M for masses. And that would just be really obnoxious. So we stuck with the traditional B. B is a magnetic field. Sometimes you'll see it as an H. Just go with it. In this class, we'll stick to B. This is a magnetic field. It is a vector. And into this field, I'm going to put a charged particle. Okay? Now, charge is equal to plus Q and I'm going to give I'm going to at least have the opportunity to give my particle a velocity. In this case, I've put it in 0 meters per second, so it's just sitting there. Okay, something interesting happens. Well, okay, maybe not, but something interesting will happen. We can talk about now a force that will be exerted by the magnetic field on this charged particle. Turns out in this case, it's exactly 0. That might not be surprising because at some point, what in the world do magnetic fields have to do with electrical charged particles, right? We're talking about different things. Why would I expect anything different? So this is probably not that surprising. Okay. Let us give this, I'll put the charge there. Put it there. Plus, let me give this charge a velocity to the right. Some non-zero velocity to the right. Okay? So, in other words, parallel or collinear with the magnetic field. What about that? Turns out I still get a magnetic force of 0. Still, maybe not surprising. Okay. Well, just for the sake of being complete, let me flip it around and give it a velocity to the left, anti-parallel to the magnetic field. In this case, I still get a magnetic force of 0. What I'm getting is something, I promise. Okay. Still maybe not surprising. Okay, let's make it surprising. Let me give this thing a velocity up. I now no longer get a magnetic force of 0. There is now a force applied to that charge. That should be surprising, but it doesn't stop there. What's not surprising, let me take off the equal sign. This force we will find is proportional to the strength of the field, of course. It's proportional to the charge, the magnitude of the charge. That's not surprising. If a force exists between two objects, we'd expect the physical parameters of those objects to govern the force, basically. It's also proportional to the speed of the charge. That's very strange. It's also proportional to the angle made between the charge, I should say, between the velocity and the magnetic field. That's very strange. But why in the world would it be proportional to the angle? Maybe it's not surprising once we figured out that if we were parallel or anti-parallel to the field, we got no force. But as soon as I go perpendicular, I get a force. Turns out there's a spectrum there. I get a force that decreases in strength as I get closer to being parallel and reaches a maximum when I am perpendicular. Okay? It's even more surprising. The direction of this force is always exerted perpendicularly to the velocity vector. That's just weird no matter how you slice it. And this is not like anything we've seen, well, sort of. It's not like it definitely doesn't work like gravity works. Gravity exerts a force towards the center of mass of the object. Electrical forces are exerted along a line of action connecting the centers of those objects, the centers of charge. We've never seen a fundamental force that exerts forces at right angles. We've seen some forces that do that. Back in 1600 when we were talking about uniform circular motion, right? There is a force that is always perpendicular to a velocity. We called it the centripetal force, right? But that's not a natural, I mean, centripetal is not a fundamental force. Centripetal is just a coordinate system, right? Like x and y is a coordinate system. This is a fundamental force exerted at right angles to a velocity. That's very strange. And at some point, some of you are going to ask me why that's the case. And I'm going to have to tell you that that's just the way the universe is. I don't know. Now, given that information, we can describe it, which is really the role of science to begin with. Science is not here to tell you why the universe is like it is. Science is here to tell you that given this universe, can we describe it mathematically? And it turns out we can, right? So I have no idea why this occurs. On some level, that's not a question science has the machinery to answer. But can I describe it and make predictions with that information? Yes. Okay. How do I put all this stuff together? Well, okay. Let me recall to you some calculus we did at the very beginning. The magnetic force acting on a charged particle is equal to this. Q, V, where I'm writing V as a vector, cross P. Remember our definition of cross product, right? It takes two vectors, throws away the parallel components, and only keeps the perpendicular ones. Then it adds to it vector notation that gives the vector that comes out of the cross product as being mutually perpendicular to both the vectors that went into the cross product, right? That's exactly what's happening here. I'm getting a force that is perpendicular both to the velocity and the magnetic field itself, right? I didn't say that well, I just said velocity. Turns out it's mutually perpendicular to both. The velocity and the field, being vectors, two vectors, automatically define a plane, right? Any two vectors are sufficient to define a plane as long as they're not collinear. These two vectors automatically define a plane. The force will be normal to that plane. So the definition here is used in what a lot of books in your formula sheet give you as the definition, the scalar definition of the cross product. Right? I don't particularly find this helpful. You're all writing it down, and that's fine. I don't find this very helpful. Because here's why. This is a scalar, right? They've taken away the directional information. The problem is, scalar multiplication is commutative, vector multiplication is not. QV cross B is very different than B cross QV. Maybe not very different, but it's different. And so, this definition is okay. It gets compounded because theta is defined really specifically for the cross product. It's an angle that runs measured positively, that is to say counterclockwise, from B to B. I don't find any of that really handy for me personally. I don't like that. I do this a different way. way, and I think most of you probably would prefer to do it a different way too. So you're going to see this definition in your book on your formula sheet. There's nothing wrong with it, I just don't particularly find it helpful. And especially since we know how to do a cross product, we can get out of it. Okay? Now, let's talk about some of the ways this can, some of the pitfalls you might find. First pitfall would be getting the order backwards, right? How it works. Also, Q could be negative or positive, right? Q itself could be negative. So, what do negative signs do for us in physics? Direction. So, if you find that a particular force on a positive charged particle, let's say is up, the force, if the charge were negative, would be down. Right? So the negative sign that could come into your charge will flip the direction of your force. This also means we can't deal with two-dimensional systems. We have to deal with 3 dimensions now. That's difficult on a board because a board, by definition, is a two-dimensional planar surface, right? So we've got to get some different notation. So let's take care of that real fast. You're used to seeing this as a vector symbol for a vector pointing to the right. Nothing wrong with that. All of our normal vector symbols are still going to be around. We've got to add to it this circle with a dot in it. You can think about this if somebody were to say fire an arrow at you, right? Hopefully they don't, but maybe. I've got kids, they fire arrows all over the place, right? They're really dull arrows, they can't hurt anything. But you know, you come to my house, you might see this happening actually coming at you, right? So you can think of it as the point, the tip of the arrow that's coming right at you. So this represents a vector pointed out of the page or board or screen or whatever you're doing. Right? It's a vector that's coming out. So from your perspective, this vector would be coming straight out at you like this. It's perpendicular to the board. Now on the back side of the arrow, if you've ever done any archery, you have flets, right? There are usually 3 of them, but let's imagine that there are 4. We're going to have this symbol, which you can imagine you're looking at the back side of the arrow as it's going away from you. This is a vector pointed into the page or board or screen or whatever. So this is how we're going to deal with 3 dimensions here. All right. Now, actually doing the cross product can be unwieldy for a lot of problems that you might come up against. In this one, probably not. We're going to stick to mostly vectors that are perpendicular, or if they're not perpendicular, they're easy to handle as far as the angle between them. But there's a neat little trick that's going to give you some answers really quickly that you might not be able to get in other ways. It's called the right-hand rule. If you've ever studied Cal 3, you've used it. If you've ever done cross products, you've used it. Now I say it, there's like 3 different versions of it. So I'm going to give you my version, which is different than your book's version. I think of the 3 versions, I think 2 are good and 1 is pure crap, and that's the one they give you in your book. If you like it and it works for you, don't change. Keep doing it, it works. If you've learned the right-hand rule is way different than what I'm going to tell you, forget what I say and use your way. I don't care. But this is the way I do it. It's the way I understand it. To determine the direction of this resultant vector, right? This guy, to determine the direction, here's my steps for the right-hand rule. 1, point your fingers. And for this exercise, these are your fingers and this is your thumb. Yes, I realize your thumb is a finger. But let's just forget about that for a second. These are your fingers and this is your thumb, and never the twain shall meet. Point your fingers in the direction of V. The first one, point your fingers in the direction of V. Once you've done that, curl them, right? Most of you, all of you, I hope, only can curl your fingers one way, right? That doesn't work. Curl them this way. This is what I mean when I say curl. Like you're grabbing onto some handlebars. Curl them towards do this in a second, so y'all see where I'm going. Step 3. Stick out your thumb. Alright, so I'm going to find some velocity vector, stick my fingers into it. I'm going to then curl them into the direction of the B field, and then I'm going to stick out my thumb. Okay, so however I have oriented, I have my right hand out here. And now, step 4, check the charge. Invert your hand. If negative. What does the word invert mean? Take what's on the bottom and put it on top. That's what invert means. So if my thumb looks like this after step 3, I just flip it over. If my thumb looks like this, I flip it over, right? Invert my hand if it's negative. Now finally, thumb gives the direction of the force. This is the right hand rule for forces. There is another one that we'll use for fields, but that's later. This is the right hand rule for forces. Okay. Everybody have it written down? That wants to write it down. All right, let's do some examples to see how it works. Let's start out with this one. Oh, I should do that. Let's start out with this one. I have a magnetic field to the right. My velocity is up. I have a positive charge. Okay. Fingers in the direction of the velocity. Just like this. Curl them towards the direction of the field. Well, the field is that way. So I'm going to have to rotate my hand around and curl them this way. Right? So my fingers are now curling into the direction of the field. So fingers in the direction of the velocity. Orient your hands so that you can curl them in the direction of the field and stick out your thumb. If you're doing it right, your thumb should be going this way, right? Into the board. Now I check the sign of the charge. It's positive, so I don't do anything. So my thumb now tells me the direction of the force. That means the force on this charged particle into the board. Okay. Does that make some sense? Let me give it another one. This is your magnetic field. Alright. I've oriented myself so that the magnetic field is pointed into the board. And I'm going to put in a charged particle. Let's make this negative, minus Q. We'll still have a velocity to the right. Now, take my fingers, point it in the direction of the velocity, and curl it into the direction of the field. In this case, that's into the board, so I'm in the right position. I just curl them this way. Right? Stick out my thumb. My thumb is going up. I look at the sign of the charge. It's negative, so I invert. My thumb is now going down. That gives me the direction of the force. And so on and so forth. Again, if you learned a different right hand rule, feel free to do it. Please do not use your left hands. There are left hand rules, but don't use them. Just put your pencil down, that'll be okay. Right? Those of you that are left-handed have a distinct advantage on exam. You can keep doing it while you keep writing. The rest of us have to put our pencils down. It's entertaining for me though to watch y'all take exams because it's like doing some strange sign language. It's the right hand rule for forces. We're going to use it a lot, not just for particles, but for currents as well, because currents are just movements of charged particles. Okay, questions about that? All right. Now, let's talk about, let me keep the field as it is, and make it bigger. Make it feel a little bit bigger. partially charged particle plus q with a velocity. I got it. All right, y'all do it. What direction is the force?
Straight up.
Say it louder.
Straight up.
Straight up. Straight up. So, in the position in which I've drawn it, there's the force. Now, this particle has some mass. Therefore, the force exerted on this mass will produce an acceleration. What is that acceleration going to do? Is it going to speed the particle up? Or slow it down? Or neither of the above? Notice you have a force exerted perpendicular to its velocity. That means the acceleration is perpendicular to the velocity. At some point in 1600, you talked about the relationship between acceleration and velocity. And probably your teacher did this looking like a windmill, because we all do. Like, if your velocity is this way and your acceleration is this way, you slow down. If your velocity is this way, your acceleration is the same direction, you speed up. What happens when they're perpendicular? Well, not nothing, there's an acceleration. But you don't speed up or slow down. There's only two ways you can change your velocity. What's the other way you can change your velocity? Speed up, slow down? That's not stopping you while slowing down. Come on. Hadn't been that long. How many accelerators are on your car? Gas pedal. Brake. Steering wheel. Right? Acceleration is a change in velocity. That does not mean speeding up or slowing down exclusively. It can. A turning, right? A change in direction is an acceleration, right? Absolutely. So, an acceleration exerted perpendicular to a velocity does not speed you up or slow you down. It just turns you, right? We talked about that or y'all talked about that in 1600. I talked about it last time I taught it, right? In the context of uniform circular motion or centripetal forces, right? What keeps the Earth in orbit around the sun? A centripetally directed gravitational force. What keeps a ball that you tied to a string whirling around your head? A centripetally directed tension force. Centripetal is just towards the center, right? It's just a coordinate system, like X and Y is a coordinate system. Centripetal is just a direction. But in this case, that's what this turns into, because it's going to accelerate but not speed up or slow down. What that means is you don't change the magnitude of the force. I keep losing my chalk. Where's the chalk?
Clear box in front of it.
Say what? Ah, thank you. I'm glad y'all are paying attention. It doesn't change speed up or slow it down, but it will turn it. So at some point later, you're going to find the charged particle here, right? It's turned it. Let's do the same thing, and the velocity will be here, right? It's tangential at this point. Well, let's do the same thing. Fingers in the direction of the velocity, curl them into the direction of the field, stick out your thumb. I get a force exerted like this. Mutually perpendicular, right? So what we're saying is this always has to be a right angle. All right, it's gonna keep turning. Later, I'm gonna find the charge here. Velocity looks like that. Force looks like that. And I haven't drawn it very well, but if you do it right, all those forces are pointed toward a specific point. The thing is just going to start orbiting because it's got a force that's always exerted perpendicular to the velocity. So when it enters the field, it just starts moving in a circle. It's going to exhibit uniform circular motion. Let's see if we can develop an equation to talk about it. We gotta go back, think about 1600 for a second, right? I know nobody likes it. In the centripetal tangential coordinate system, you had this expression, the centripetal acceleration, which just means the acceleration towards the center, can be expressed like this.